All right, so we're looking at a question 2021, starting with question 1. And as you would recognize, it says do not spend more than 30 minutes on question 1. So we're getting right into it. Now, question 1 is focusing on electrolysis. Now, it says a student conducted an experiment to determine the products formed from the electrolysis of aqueous copper 2 sulfate using inert electrodes. Figure 1 shows a simplified diagram of the apparatus. All right, so we're seeing the aspects of the setup of the electrolysis. We're seeing P, Q, we're seeing the battery, we're seeing the copper 2 sulfate aqueous, we're seeing the ammeter. This is what we use to check the current flowing through our circuit. And just to have a brief discussion as to what is happening. Now, one of the things that we want to do for electrolysis is to ensure that the ions, whether the cation or the anion that is going to be in the electrolyte, would have been mobile. And so before you place any substance in it for you to do the decomposition, it needs to be in a state where the ions are mobile. So CXC will make mention of it being aqueous. And once it is aqueous, it simply means that what they have done is to dissolve that salt, copper 2 sulfate, in water. If it is that they say molten, then they would have caused it to melt. Now, when you use aqueous, it doesn't only have those cations present, and I think questions that follow will probably even ask you things like that. But just to give you an idea, a little recap of electrolysis. So in this case, the electrolyte, we're seeing P and Q, and these would have been considered as our electrodes, and their function is to carry current into and out of your electrolyte. An electrolyte is a substance that really allows current to flow through it, and the current flows due to the presence of the ions, right? So when we basically dissolve this copper sulfate in water, you're going to have your copper ions, you're going to have your sulfate ions, but also coming from the water, you have your hydrogen ions and you have the hydroxide ions. So when you basically set up the circuit in such a way, one of the things that you want to be able to note is that from your power source or battery, it has both a positive and a negative side. Now, this is key in identifying the different electrodes that are present. We know we have two of them. We have the anode and we have the cathode. Sometimes students ask me if they are on a specific side. No, we denote or know the different electrodes based on the side that they're connected to on the battery. So the positive side, that's where we find our anode. So right away, once you're a student and you understand electrolysis, you would have recognized that P is the anode. Now, reason being, it will basically have the power source or the battery pulling electrons from P. Now, just as though when electrons are lost from a metal, the metal will now assume a negative charge because we know that the electrons are, sorry, it will assume a positive charge because we know that the electrons are negative. And so it is the same concept with our anode. Once this circuit is on, electrons are going to be pulled from the anode, causing it to now assume a positive charge. On the flip side, electrons are going to be forced onto the cathode, which is Q. And similar to how a nonmetal will react, once they accept electrons, the nonmetals become negatively charged because you now have more electrons than protons. So one thing to remember, the anode is connected to the positive side. CXC has a tendency to sometimes orient the diagram in different ways. So don't think that the anode is always going to be on the left or on the right. It can be oriented upside down. You have different ways of presenting, but once as a student you know that it is connected to the positive side, then you know that electrode would have been the anode. Now, with that being said, when you know that opposite charges will attract, and so because the anode is positively charged, we have some ions that are present in our electrolyte. I didn't indicate them, which I can do to the side quickly. So here we know we would have had our copper ions. We would have also have our hydrogen ions. We would have had our sulfate ions, and also from the water, the hydroxide ion. So these are the ions that are going to be present in our electrolyte. And as you can recognize, we should know as students that we have cations, which are positively charged, and anions, which are negatively charged. Now, because the anode that we mentioned here is positively charged, what it will do is to attract the negatively charged anions. And if you notice, there's some correlation between the name of the electrode in terms of what ions are attracted to it. So the anode attracts the anions, while the cathode, of course, coming from cations, it's negatively charged, so it's going to attract these cations. But there are three things that you have to consider when you're looking at who is basically preferentially discharged at either the anode or the cathode. Like I said, I'm just doing a quick recap. So we know that we have the electrochemical series that places these ions in a reactivity series where the one that is lowest in the series would be the one that is preferentially discharged. So that is one way. And there's a chart. You can go in your textbook on the internet. Probably can write it to the side later on. We basically use that to determine who. So for your anions, there's a electrochemical series for them. For the cations, there's also one for the cations. Do remember, in terms of the reactivity of metals, in terms of electrochemical series, we have calcium coming before sodium in that series. The other thing that will help or determine what is discharged is the type of electrode. Now, we basically have two types of electrode. We have inert and we have active. Now, in the question, they did say that they're using inert electrodes. And I think there's a question that will ask you what. But graphite, carbon, those are the popular inert electrodes that we use. So either the electrodes, once you hear inert, it's usually made out of graphite, which is also a form of carbon, right? And so that denotes inert electrode. If you're going to have an active electrode though, once you have the electrodes, they should have the cation that is present in the electrolyte making up that electrode. So since we have copper 2 sulfate, in order for me to have an active electrode, then the electrodes would have been made out of copper. So that's another criteria to determine which ions are discharged. The other thing, final, is the type of electrolyte. So if we had molten, then we only have the anions and the cations from that salt that you basically melt. And it wouldn't have any hydroxide or any hydrogen ions. Also, if it is that they use the term concentrated, when you have concentrated electrolyte, say for example concentrated sodium chloride, once there is one of those halogens present, they are the ones that are going to be discharged at the anode. So if you have concentrated and the anion present is one of which is the halogen, whether iodine, bromine, or chlorine, then they will be discharged. It overrides the electrochemical series because technically the OH is lower than all of those in the series if you look at that series. So you can pause and you can basically bring up that series and you'll recognize that the OH is actually the lowest in that series. But if you have concentrated of the solution where you're using a halogen, lead bromide, sodium chloride, lead iodide, those would be a situation where the halogen is going to be selected at the anode. And of course, if it has dilute, then that is the time you have the hydroxide being discharged, right? So we should take that into consideration. Now, a lot of times students ask, is that also related to the cathode? No. In terms of the who is discharged at the anode, it is based on the electrolyte, the state of it. If you're dealing with a halogen, then when you come on to the cation, we still follow the rule of the electrochemical series. So if you know anything about the series, you would have known that copper falls below hydrogen. So it would be selected, right? So we have said quite a few in terms of this, and I just want to also indicate that copper sulfate, if you type that in, it's that it gives a blue solution, which is also very important when you're looking at certain questions provided by CXC. Now, a current was passed through the electrolyte and the starting time was recorded at 10-minute intervals for 1 hour. The volume of oxygen gas evolved at the mass of the mass of copper deposited is measured. At the end of the reaction, the total mass of copper deposited was 4.85 grams. The volume of oxygen gas evolved is shown in the table. So looking back at the setup, what would have been happening in this case, because we're using inert electrodes, could be made out of graphite, carbon, we know both of these would be basically attracted to the anode, but only one of them would be discharged. When you look at the series, the hydroxide falls below the sulfate ion, and so it is the one that is going to be preferentially discharged. And when that is discharged, one of the things that you'll be getting is the oxygen. And that is what they're basically collecting and recording every 10 minutes. So let's go back down to look at the table. It says volume of oxygen measured at 10-minute intervals. So for the first 10 minutes, we had a 2.4 centimeter cube, right? 20 minutes, we saw 3.6, 30 minutes, and we're looking at the figures. Now, for the first part of the question, it says define electrolysis. So what is electrolysis? All right, so we can say this is the decomposition by the passage of electric current. In other words, we basically want to break down a substance. Let me just increase the size. So we really want to break down the substance, and it is a means of obtaining ions or obtaining substance that would not have basically, you wouldn't be able to collect these items just like that. And I can switch to sodium chloride and talk about it quickly. If sodium chloride, if you can recall, how did that bond occur, is when sodium basically gave up an electron to chlorine. And we know that elements tend to bond to try and reach that level of stability. And so the chlorine, and while the sodium gave up the electron, it became positively charged. While the chlorine accept the electron, it became negatively charged. We had that positive cation, negative anion, and the charges attract each other. Now, this type of bonding allows for those elements to become more stable. And since they're stable, they wouldn't want to revert or go back to their instability. But if you have sodium chloride and you want to get back the sodium and you want to get the chlorine, we're saying you can use electrolysis, pass the current through it, and it will basically decompose or break down, separate, where you can get the sodium and you can get the chlorine. So naturally, if you have salt, table salt, you can have it in your counter for years. It will not decompose. It won't break down. It won't spoil. You can have it in there for years on top of years, and it's just going to be there. So it is a good way to retrieve the compounds that would have been formed after the whole bonding process. So leaving sodium chloride, it's not going to go back to sodium and chlorine because at that stage they were unstable. So just one material that could be used as an inert electrode in the electrolysis of aqueous copper 2 sulfate. And we just spoke about this we would have indicated that graphite is one of those inert electrodes. Graphite. Let me just increase the size. It says, using the data in table 1, plot a graph of volume of oxygen measured versus time using the axis in figure 2 on page 7. Draw a line of best fit, and we would have had a graph. So I'm jumping to that graph to deal with, say, so for the 10 minutes, it would have been 2.4. So 2.4 would have been somewhere right here. Sometimes when the information, the table, is on a different page, to maximize on time, remember they say don't spend more than 30 minutes. One of the things that you can do is to write down the information so you can quickly, because even with this you would be skipping back. You can just write it down on the page of the graph, not on directly on the graph anywhere, but to the side where you can basically look at it. Because even for me, I'm going back up. So 3.6, 4.8. So 3.6, somewhere right there. 4.8. The next two would have been 6, 7.2. We have 7.2. And then finally 8.4. All right, I kind of bring it down just to be able to get that best fit line. So this is what your graph would have been looking like. Maybe it's a little bit off in terms of. So I'll go for my ruler, and this is what you would do in the exam. So Microsoft Word has this feature with the ruler a lot of persons don't know. that you can utilize it. Right. See if I can draw this line. And it should give me something looking like that. Now, maybe the point is too large. So let me use for persons to see. All right. And it's a little bit out of line. All right. So it's a little bit not, I wouldn't be able to move because I stopped when I started this line. So it's not a full line in terms of going through the best, drawing the best fit. But when you're in the exam, remember to carry a ruler, and that is what you would have done to ensure that as much as possible, the points go through as much of, well, the line goes through as much of the points as possible to get your best fit, right? Let me just increase. All right. So that would have been your best fit. You would have been given 5 marks to draw it properly. The next part of the question says use the graph to determine the time it took for 5.5 centimeter cubes of oxygen gas to be liberated. And this, as you know, would be at the anode. So what you do now, 5.5, you look at that, identify 5.5 would have been here, right? And you now take it to the time. And just like that. And so we know this would have been 35, 36, 37. So approximately 37 minutes. It says identify all the ions in the electrolyte used in the experiment. And if you can recall, by memory, we said that it's aqueous. And so all the ions that are present, we have our copper 2+ ions. We have our hydrogen ions. We also have our sulfate ions. Finally, we have our hydroxide ions. P and Q are electrodes shown in the apparatus used for electrolysis in figure 1 on page 5. State which electrode is the anode and which is the cathode. And I did indicate that they might have, carried a question the moment I saw that they were labeled. And let me just bring it back. And guys, remember, wherever the electrode on the power source, and in this case it's a battery, so if it's connected to the positive side, P would have been the anode, and since this is connected to the negative side, then Q the cathode. So P anode, and we said these electrolytes, well, electrodes rather, they are responsible for taking current in and out of the electrolyte. And we said Q is the cathode. We said that we can remember, look at the name itself. So what it will do is to attract the anions, the cathode. Name again, what it will do is to attract the cations. And just let me just indicate right here, this is negatively charged and this is positively charged. Now it says state one ion in the electrolyte that will drift towards the anode. And I indicated right here that we have two basically going towards the anode, but they ask you for one. So any one of them, you could have mentioned whether you take the OH ion or the sulfate, even though both of them are going towards the anode, it is because, in fact, that they are negatively charged and the anode is positively charged. But as we said, only one will be discharged. Now, the next part, it says, write any one of these. You don't have to give both. They said they did indicate one. I'm just ensuring that, we get the full. Now, we also mentioned earlier that when you look at the situations or the criteria that determines who gets selected, one of the things we said is the reactivity series, right? So the reactivity series is one which determines, especially when you're looking at the cathode. When it comes on to the anode, we have other things, whether the dilute or what you would have referred to as a concentrated solution, and also if we're using a inert versus active. So in this case, we're using inert, and when you look at the electrochemical series, hydrogen is directly above copper. So copper is lower in the series than hydrogen, which simply means that the copper ions are the ones that are going to be preferentially discharged. So we have the copper plus ions, right? And just to be fair, we want to indicate that we have the aqueous. They did ask you for an ionic equation. We have, let me just carry this a little bit more. What really happens, and I can go back to the top a little bit. When the copper ions come close, because the copper is attracted to the negative charge of this cathode. Now the cathode would be receiving electrons. Remember, copper 2 plus as a student, you should know that what would have happened to copper for it to become 2 plus is that it would have lost 2 electrons. And so it now has 2 more protons than electrons, and that's why it has that 2 plus, that positive charge. Now, when this ion drift towards the cathode is going to now force back electrons on this copper ion, because in this case we are trying to ensure it goes back to the atom state, because remember, that's how we want we really decomposing. We want to get it back to how it was. So before this copper gave the 2 electrons to that sulfate in order to remain stable, we're now saying, copper, take back these 2 electrons. And when that happens, you now get copper solid. So the copper, let me just find an arrow. My arrow is a little bit. So we're now ending up with copper. This is going to be solid, and that's why they would have spoken about the mass of copper being deposited. Now, in terms of the experiment, one of the things that the student can do, or the persons can do carrying out the experiment, is to get the mass of the electrode before they start, and once they do the whole electrolysis for a period of time, they would have to remove the electrode and then wait to obtain the new mass, and that would have, you subtract the initial from the final to get the mass of the copper that was deposited. That's a way of doing it, right? So this copper is really moving from the copper ions to the copper atom. Now remember, one of the prerequisites of electrolysis is your oxidation and reduction. And so sometimes CXC may even ask you, what is happening at the anode, what is happening at the cathode? This 2 plus simply means that the copper has a +2 charge in terms of oxidation. Once you have a neutral atom, then the charge would have been 0. So the charge right here for the copper is 0. If I'm moving from a 2 plus to 0, it means that my oxidation number is decreasing. And since my oxidation number is decreasing, it then therefore means that reduction is happening at the cathode. And overall, once you have electrolysis, reduction is always happening at the cathode. Now, another way that you can look at it in terms of electrons, we know we use this phrase rig, and rig is reduction is gain of electrons. Now, what was the copper 2 ion doing? It was gaining 2 electrons. And so again, it denotes reduction. Now, here, and I use this concept, how many electrons? We know 2. And oftentimes students ask me, where do we put those electrons? Remember, you have a right hand side and you have a left hand side in terms of your reaction arrow. Now the electrons, if you are carrying out reduction, then we put the electrons on the left hand side. If it is oxidation, we write the electrons on the right hand side. So since we are doing reduction, this is what your reaction, your ionic equation will look like. And once you get to this, it is very important to note what is the relationship in terms of moles. So we know if you have a coefficient in front, or if you're not seeing a coefficient, there's a 1. So every 2 moles of electron, right, you will basically get 1 mole of copper deposited. So every 2 mole of electron, there's 1 mole of copper. And it's basically coming up in the next question that we'll have to use this information. Mr. Faraday says 1 electron, in terms of the charge, it's 96,500 coulombs, right? So they did ask you, calculate the quantity of electricity that passed through the copper sulfate solution when 3.5 amp of current flowed for 1 hour. Remember, they are checking using the ammeter on the diagram to see the amount of current. So CXC made it easy. And I say to you as students, once they give you some information, quantity of electricity equals the current times the time, right? So Q equals IT, and the time would have been in seconds, right? It's very critical that you remember that. So when we look here, so we have Q increase, so Q equals IT. We said Q, I is the amp, 3.5 times, so we have 1 hour. We know 60 seconds make a minute, right?
Yes, sir.
All right. So when you work this out, grabbing the calculator, and remember to take the calculators to the exam. Get familiar with the calculators. So we would have gotten 12,600 coulombs. So this is a charge that is going through. It did say calculate the number of moles of copper deposited. So when we think about this, we go back to here. In order for us to get a mole of copper, we would have needed 2 moles of electron. Now each electron gives you 96,500 500 coulombs. So we use that as our conversion factor. So let me input that. So when I have 1 mole of electron, that is equal to 96,500 coulombs. But that is why it's important for us to do this equation. So we do have 2 moles of electron. So it's going to be 2 times the 96,500, which means in order for us to get 1 mole of electron, what is the current that needs to be flowing through?
Sir, 193,000.
So in order for me to get 1 mole of copper, I need that amount of charge to be flowing through my circuit. We now use this information because we know when I have 1 mole, right? In order to get 1 mole of copper, I need 193,000 coulombs, right? But for the period of time that that the students were doing this electrolysis, they had 12,600 coulombs. And for working it out, we said that this is going to be our conversion factor, right? So from that, we create a fraction. Any unit that is here, so we start by what we were given, in this case, what we calculated, and we're going to create a fraction, the same unit that is here that goes as your denominator. It's going to be over 1 mole divided by the 193,000 coulombs. Forgive me for the space that is here. I think probably I can adjust that. Paragraph, single, yes, like that, and underline just to show. And so from here, we would have gotten the information for the number of moles, because the coulombs cancel the coulombs, leaving our answer in moles. So what is the figure that we would have obtained?
Sir, I got 0.653 moles.
0.6.
653 moles. Same here.
This is moles of the copper, right? And so we would have completed by doing, so just to run through, basically when they say calculate the number of moles for any, either they can take 2 approaches when given these questions. They can ask you to calculate the mass at the, in this case, deposited at the cathode. They can ask you for the volume of gas. Now you need to remember your relationship between moles and volume of gas, moles and particles, moles and mass. Now the thing is, whichever route you're going to take, just remember what you need to do. Now when we were doing this question, remember the half equation happening at the respective anode or when in this case the cathode was very vital because it determines how many moles of copper you obtain, how many moles of electron you basically use to get that mole of copper. So in moving on, it says calculate the mass of copper deposited given that the relative atomic mass of copper is 64. Now, as always, some persons can look and determine, but I love to always do the full, explanation along the line. Now, what is the relationship? 1 mole of, since we're dealing with copper, we're talking about element. And if it's an element, we use the term atomic mass. And so students sometimes ask me, how do I know when to use atomic mass, when to use formula mass, when to use molecular mass? It's based on the item or the substance you're dealing with. Now for covalent compounds, so we know that oxygen gas, hydrogen gas, those are covalent compounds. We will use the term molecular, right? Because they're made up of molecules. Elements are made up of atoms, so we use atomic mass. And we find the atomic mass on the periodic table. Copper falls out of the 20. So in this case, what CXC did was to provide you with the atomic mass right here. So just for the benefit of somebody who might have not known, if you're dealing with the ionic compound, where, say, for example, copper sulfate, it would have been 1 mole equal to the formula mass. And for those, you basically add the amount of atoms that make up the compound to get that, right? So just a little insight. Once you get to this point, you would have made the connection that really and truly 1 mole is really equal to the 64 grams, right? Let me see if I can reduce the spacing again. And because of this, we go back to the question that we just completed. We know we don't have a mole. We have 0.653. And once we indicate that, we know we're going to be multiplying this and we said from this here we get a fraction, we create a fraction from this, and what goes to the denominator is based on what unit is here. So a lot of times students like to just write numbers alone, and even for some questions persons tend to not give the units. So if it is that you stop right here and just say 0.653, sometimes that is what causes you to lose a mark because you want to make mention as to the unit. Is it moles? Is it mass? Is it particles? So it's very important that you put the units when you're doing these sort of calculations, especially if it asks you to show working. So we said that we're going to have that 64 grams and the denominator we're going to have that 1 mole. Now a lot of persons may use the cross multiplying method. Don't have a problem, you can use that going into the exam once you're used to it, but with this it eliminates any mistakes. Sometimes students ask, when do I divide? When do I multiply? So the moles cancel your moles, leaving your answer in grams. And they did ask you for the mass. So when we work 0.653 times 64, What is the mass we get?
So I get 41.79 grams.
That sound too much.
Let me go again.
Sir, that's what I got.
0.653
Times 64.
times 64. Yeah.
All
I
right,
get 41.792.
let's double check the 193.
So that's
Sir,
it.
divide. When you go back upstairs to the 12 point, not the 12 point, it's 12,600 divided by the 193,000. I'm kind of confused or we get the 0.653, no 0.0653.
No, 3, 1, 2, 3. Yeah, 0.0653.
Okay, so that's where and even with that, it's good that we were doing it and we saw, because right here it couldn't be that we're getting that amount of moles when we're really not that amount of mass, right? When we're not even at a certain moles. But this is showing us that we have to do the double checking sometimes. So thanks. So this would have been 0.0653. So this should have been a red flag to us even when we got it, because this is a little bit half mole, which really wouldn't be possible, right?
Yes, sir. So the answer would be 4.18 grams
Wonderful. So 4.18 grams, sorry,
per,
of,
no, what was on? Grams.
of copper. We did make that adjustment to the number of moles. All right, so it says suggest one reason for the difference in the mass of copper calculated in D and the mass measured by the student. So remember, they, in terms of theory, would have gotten 4.85 grams. But when the student, did it, we basically have, or when we actually calculated, we saw 4.18, but when the student did it, we see 4.85. What could be a difference in terms of the mass calculated? Now, when you're doing the electrolysis, as you note, the electrodes are basically, in the electrolyte. They're in that solution. And so when the student may have removed, it may still have some amount of electrolyte on it that would have given an incorrect or a higher reading based on the fact that the student may not have dried or gotten the correct mass, because there might have been presence of the liquid still on that electrode. So it's not giving a true reflection of the actual mass of the copper itself. So one thing is where they're now doing the actual weighing, it's not going to be the exact as if we are doing the theory calculation. So the theory calculation gives you to a close proximity because it's not taking into consideration errors such as incorrect weighing or water or fluid still being present on the electrode that the student is obtaining the mass of the copper from. State the color change that would have taken place in the electrolyte after a few hours. Now, the change. We know that the solution is blue, and while copper is now being deposited from the electrolyte onto the cathode, it's removing the amount of copper, and copper is one of those ions that give you that blue precipitate or that blue solution, or the solution appearing blue. So since copper is being removed, the solution will get a pale blue appearance. The student was asked to use the same electrolyte to purify a piece of impure copper. State how the electrodes in figure 1 on page 5 can be modified to obtain pure copper from impure copper. Now we know that one application of electrolysis is for purification of, in this case, they're talking about metal. So to purify a substance, a metal, we can use electrolysis. And so let me go back to the diagram. So the modification that we would have now do to this to get that purification occurring, instead of this being made out of graphite, we would have placed the impure copper substance, right, at the anode. I was going to say, if we can, like that. So the impure copper material will be placed on the anode. That's one modification. The next thing that we would do is to basically make the cathode out of copper. And so earlier on we spoke about this. Now what you would have is a active electrode. Active electrode, the electrode is now going to take part. So really and truly, in this substance, or in this copper, impure copper, you have substance that is not copper, and that's why it's impure. Now, when you have an active electrode, there is no ions that are going to be discharged at the anode. Instead, the ions are going to fall out of this copper, out of the electrolyte, or into the electrolyte rather, causing the anode to decrease in size. So the copper and the impurities will fall into the electrolyte as it breaks down. So copper ions are going to be added, and you'll now see the impurities falling into the electrolyte. The copper will still be sent to the cathode, where you know in the end will have a pure sample of copper, because only the copper is going to be deposited at the cathode. The impurities will be in your electrolyte, and so that's how we basically have a purified or a pure sample of your copper metal. Now with this, if CXC asks, because just for benefit, the solution will not have a change in its appearance like before, because as the copper ions are basically deposited on the cathode, then you have copper ions falling into the solution. So it still have a blue appearance as the time progresses. The anode is going to decrease in size, the cathode increase in size. None of your anions basically would be discharged at the anode. So you're still going to have your sulfate and your hydroxide ions present in the electrolyte, right? So that is how you go through the concept or the modifications that you would have had for the purification of the impure copper.